I'm Matthew Hall at Bromley Emergency Courses, and in this short video tutorial, the last one in our series on the immune response, I want to talk about immunoglobulins. In the previous video tutorials, we've discussed the innate immune system and also the adaptive immune system. And within adaptive immunity, we talked about how antigen is presented, how an adaptive response is generated, and also about the two branches of the adaptive immune system, the humoral or antibody-mediated response and the cellular or T-cell mediated response. But we didn't talk very much about immunoglobulin. So for the next couple of minutes, we'll fill that gap. So immunoglobulins are multimeric proteins, essentially, produced by plasma cells. Remember, plasma cells are differentiated B cells, and the immunoglobulins are really the weapon of the humoral immune response. Immunoglobulin may be membrane-bound or secreted, where they may be found in the extracellular fluid, the circulation, or on mucosal surfaces. Technically speaking, antibodies are a subclass of immunoglobulin, but often the terms antibody and immunoglobulin are used pretty much interchangeably. There are 5 main classes of antibody: IgA, IgD, IgE, IgG, and IgM, and each class has a different tissue location within the body and a different role within the humoral response. But all classes of antibody have a common structure and function. Here we have a stylized drawing of a typical or generic antibody. It is a multimer of 2 light chains, that's one light chain, there's another light chain, and 2 heavy chains, that's one heavy chain, and there's another heavy chain. The light chains and heavy chains are joined by disulfide linkages at several locations, and the chains have a carboxyl group at one end and a amide group at the other end. That's the basic structure. Now functionally, we need to note that the antibody molecule, can be divided into 2 sections. Firstly, here at the terminal end of the antibody arms, we have the Fab fragment, and the Fab fragment contains the antigen binding sites right at the terminal end of the arms. And because the antigen binding sites on each antibody are unique, recognizing only a single specific antigen, their appearance and structure differs between antibody molecules, and so the Fab fragment is referred to as being variable. And of course it is at the antigen binding sites that the antibody attaches to its specific antibody on target pathogen. At the carboxyl end of the antibody, we have the Fc region. Now the Fc region is constant for a particular antibody class, but differs between antibody classes, and that's because it is the effector end of the molecule. It is the region which generates the response from the immune system once antibody has bound to its target pathogen. And the Fc region does this by having binding sites for complement proteins and for macrophages and other phagocytic cells. So by understanding its structure, we can understand how this antibody functions. First of all, many antibodies will bind to their specific antigen on a target pathogen via the antigen binding sites of their Fab fragments, and this results in a pathogen coated in antibody. At the other end of the molecule, the Fc region is flagging up the bound antibody to the effector systems, which come in and neutralize the pathogen. Complement proteins will bind to the Fc region and cause direct pathogen killing via the membrane attack complex. Or macrophages and other phagocytic cells may attach to the Fc region and be directed to engulf and digest the invader. Now let's spend a moment understanding the different characteristics of the 5 immunoglobulin classes, which is summarized in this table. Firstly, their structure can differ. For example, IgD, E and G are all monomeric, while IgA is a dimer of 2 antibody molecules, and IgM contains 5 monomer antibodies in a pentamer. In terms of total percentage of serum immunoglobulin, by far and away the most prevalent is IgG, followed by IgA, secretory IgA, and by IgM. Under normal circumstances, there is very little IgD or IgE in the serum. IgG is the only antibody that can cross the placenta, and in doing so is able to provide some degree of immunity to the fetus and the newborn. In terms of function, we discussed secretory IgA when we talked about the innate immune system. It is found on mucosal surfaces in mucosal secretions of all kinds, and it acts as part of innate immunity. Specifically, it binds microbes in the mucosal secretion and is able to flag them up to macrophages and neutrophils for digestion, hopefully before the microbe has even entered the body. IgE, you will recall, is the main antibody of allergic and antiparasitic responses. IgM is the main antibody of the primary humoral response. That is to say, it is the main antibody produced when the immune system responds to an antigen for the first time, in contrast to IgG, which is the main antibody of the secondary humoral response. That is the quicker, bigger and more sustained immune response which occurs on re-exposure to the same antigen. The Fc portion of IgG can bind complement as well as attracting phagocytes. In talking about the function of IgG and IgM, we brought in the idea of primary and secondary immune responses, and I want to finish just by expanding on that a little bit because we hadn't mentioned it before. A primary immune response occurs on first contact of the immune system with an antigen. It relies on T and B cell activation de novo, and the response is usually fairly slow, taking days to ramp up. Antibody levels produced are fairly low and has a low specificity for antigen. And IgM is the main antibody produced during the primary response, though some IgG is also produced, as you can see in this diagram. And usually the primary response is waning after about 2 weeks or so, when hopefully it will have cleared the initial infection. Now, a secondary immune response occurs on re-exposure to an antigen. In other words, an antigen that has elicited a primary response already at some point in the past. IgG is the main antibody produced and released during secondary immune responses. And the response relies on immunological memory, that is memory T and B cells, to initiate a faster initial response with a much higher level of antibody, and that antibody has a higher specificity for antigen. All in all, a much more powerful response of the immune system to re-exposure to the same antigen, and hopefully that will be sufficient to eradicate the pathogen before it can cause illness or disease. So that concludes my 5 short tutorials on the immune response. They cover most, if not all, of what I think you need to know about the basic science of the immune response, and hopefully also those questions that might come up on this subject in the FRChem primary.